Welcome back. This is Lecture 3, and now we're going to move on from discussing the different types of compounds to naming our compounds. We are going to name ionic compounds and covalent compounds, but not metallic compounds. So, for our ionic compounds, the first thing to remember is that ions form an exact ratio based on the charges of the ions involved. So for sodium and chlorine, sodium forms a 1+ ion. It's an alkali metal over here at the left. It loses its single s electron. Chlorine forms a 1- ion. It's a halogen over here on the right. It only gains 1 electron. So you have a 1+ ion, a 1- ion. The charges cancel out. The salt overall is neutral, even though it's made of ions. So we have a 1-to-1 ratio of sodium and chlorine, and we call it sodium chloride. Magnesium and fluorine, you get a magnesium 2+ and a fluorine 1-. So you need 2 fluorines to balance out the charge of the magnesium. So it's MgF2, magnesium fluoride. Then aluminum plus oxygen. Notice that oxygen is diatomic. It's a molecular when you're talking about elemental oxygen. Aluminum takes a 3+ charge. Oxygen takes a 2- charge. So in order to balance that, you need 2 aluminums and 3 oxygens. Okay? So 2 aluminums gives you a total of 6+. 3 oxygen gives you a total of 6-. So Al2O3, or aluminum oxide. So the actual name is fairly straightforward so far. It'll get a little bit more complex in a bit. You have the cation first, so the positive ion, the metal, followed by the anion, so that's the non-metal, the negative ion, and then you drop the ending of the anion and replace it with IDE. So chlorine becomes chloride, fluorine, fluoride, oxygen, oxide. Okay. And here is how you can sort of figure out the ratio, okay, knowing the charges. Fairly straightforward, but I'm going to show you 2 ways just in case people are not so happy about one of them. The first and less popular way, let's go ahead and look at potassium sulfide, Ks. Okay, so here we have potassium, here we have sulfur. Okay. First, you need to know what ions they are. Okay. Potassium forms a 1+, because it's over here in the first column. Sulfur is 2 steps away from argon, so it forms a 2-. So 1+, 2-. So here is our thing. So potassium and sulfur. So potassium is going to lose its 1 electron over here to sulfur. Now, potassium is happy as a 1+. Sulfur is not yet happy. So we need another potassium. It's going to lose its 2nd electron. Now, sulfur has the 2 electrons it needs. It's happy. And we've got K2S. You can do that for any sort of compound. I'll show you some more complicated ones. But a slightly easier method would be just bring the charges down. Okay? So the 1+ becomes a 1 down here, the 2- becomes a 2 down there, and you have K2S. 1s we tend to leave as invisible. Okay. Now let's look at a more complex arrangement, magnesium and nitrogen. So magnesium is element 12 right here. It has 2 electrons. Nitrogen is element 7 over here, and it has 1, 2, 3, 4, 5 valence electrons. Let's go ahead and draw them this way. So magnesium loses its 1st electron to nitrogen and its 2nd electron to nitrogen. Magnesium is now happy. Nitrogen is not yet happy, doesn't have the stable octet. So we bring in another magnesium. It loses an electron to nitrogen. Now nitrogen is happy, but magnesium is not. So we bring in another nitrogen. Boom. Happy. Not happy. So another magnesium. Okay, and now everyone's happy. So yeah, that's kind of complicated, but some people might like the visual aspect of it. The other thing is that magnesium takes a 2+ charge, has 2 electrons to lose, and nitrogen takes a 3- charge, and you bring them down, get Mg3 in 2. So the numbers going across is fairly simple, fairly straightforward. In my experience, it's the far more popular method. Okay. But I want to caution you that you need to watch out. You need to be careful. Let's look at calcium and oxygen. Okay. Calcium is element 20, so it has 2 valence electrons. And oxygen is element 8, it has 6. So, if you're doing the number method, calcium goes a 2+ charge. Oxygen wants to gain 2 electrons, so it's going to be 2-. You bring the numbers down. If you said calcium 2, oxygen 2, you would be wrong. No. You have to reduce it. We're talking about a ratio. 2 to 2 means 1 to 1. It's calcium oxide. And that is fairly easy to see here, because calcium loses its 2 electrons directly to oxygen, making it a 1 to 1 ratio. So either method will still work. Okay? You won't get in trouble for using either one. The point is just that this, at the very least, helps explain why it's a 1 to 1 ratio for calcium oxide. So that is one complication we can get into for naming ionic compounds. There will be more later, and they will be unavoidable. So the first is come up with your ratio, and then make sure that you can't divide by anything. Get rid of the common factors, as the math would have it. So it's a 1 to 1 ratio, not a 2 to 2 ratio. Now, the thing that makes it complicated, the first unavoidable complication, is multivalent ions, which means metals that can take more than one charge. So, that is to say, the transition and post-transition elements. What you do is you have to find a way to indicate what the charge is in the name of the compound. So iron, for example, can take a 2+ charge or a 3+ charge. So iron plus oxygen with a 2+ charge on the iron. It's a 1 to 1 ratio. Iron 2 oxide. Use a Roman numeral to indicate the charge. Iron with a 3+ charge. Bring them down. 3 and 2. That means it's Fe2O3. Iron 3 oxide. Lead can take a 2+ charge. So here lead 2 chloride, PbCl2. Or it can take a 4+ charge, lead 4 chloride. Okay, so you always have to use the Roman numerals for a multivalent ion or multivalent element, an element that can take more than one charge. Okay. So, say you have scandium 3+ and iodine with a 1-. Bring it down. Bring it down. Scandium iodide? Nope. Scandium is a transition metal. It needs to be scandium 3 iodide. Silver with a 1+, and then oxygen with a 2-. Bring the charges down. You end up with Ag2O. And that is silver oxide. Nope, you do not need anything there. That is perfectly fine with just a blank space because silver can only take one charge. Silver is only ever 1+. So remember, silver, zinc, and aluminum are the 3 univalent metals that aren't over there on the left-hand side of the periodic table. So for that, it's fairly straightforward. You can get from the compound here over to the name over here, or you can get the name from the compound. But just giving you the elements with these multivalent compounds, I cannot expect you, just from the elements alone, to get to either one of these, okay? Just from the elements. You can't do that. You need to know what ion is being formed. But when you do know what ion is being formed, as with the univalent metals, or if I give you the charge on the metal, then you can get the name and the ratio. Okay, and that is what I expect you to be able to do. For a monovalent or univalent metal, where it only forms the one ion, from the element, you can get the formula of the compound, NaCl, MgO, CaO, CaF2, things like that, and you can get the name of the compound, calcium fluoride, magnesium oxide, and so on. For a polyvalent metal, I would have to give you the charge, but you wouldn't be able to go from the elements to anything else. You would have to be given the charge on the polyvalent metal, and that will let you get the ionic formula and the ionic name. So iron 3 oxide, and so on. All right. Next up, we have covalent compounds. This might be pushing it on our timer. It is. I think I'll go ahead and call it quits for this particular lecture, and we will come back and start covalent compounds in the next lecture.